Hello, so today we are going to look into a very interesting way to solve a simple problems like capacitor problem. So we will look into finite element method based approach, how to use finite element to solve a very simple capacitor problem which is a Laplace problem. So let us look into the geometry of the problem. It is a Laplace equation and in 2 dimension what we are interested is dou square phi by dou x square plus dou square phi by dou y square is equal to 0 and with certain boundary conditions that are given. So let us look at a standard capacitor, a parallel plate capacitor. So we have a top capacitor plate and a bottom capacitor plate, and there is a potential that is applied here. So let us say phi is equal to 1 volt and there is a bottom potential that is given phi equal to 0 volt. So we are going to discretize it using triangular discretization. So let us look at how the triangular grid is going to look like. So for example we are interested in using unstructured grid. So the grid is going to be very irregular. So some places you have very fine cells, in some places you have very coarse cells, and the cell size is going to depend on the gridding or the meshing software, and this is one of the things that we should be very careful. For example here you have a triangle that is very long in the sides, and there is another triangle which is symmetric with 1 or 2 sides, whereas these triangles in the middle are very fine. So if you are having a mesh generator that is not going to be very accurate, so your problem should be still be run on such outputs of those mesh generators. So we want mesh generator that is going to be very general. We cannot rely on the mesh generator's accuracy itself. What we can do is we can refine the grid, but we don't know the quality of the grid that can be produced or that will be produced by any mesh generator. That being said, the program what you are going to use or going to apply for solving such problem should be able to solve the problem using any mesh. Of course we need to look into the numerical accuracy that we need. If we need better accuracy we have to refine the grid. But what I am trying to say is, if your program is able to run on any general grid, for example any general triangular grid, it does not need to be uniform or regular, and that is a good way to start programming. If your program is dependent on the regularity or the uniformity of the grid, then you are very specific and you are not able to solve it using a generalized mesh that can come out of any mesh generator. So when I say generalized mesh, what I am pointing out here is generalized triangular grid. So once I know the shape of the grid, I should be able to run it, not to put so much emphasis on the quality of the grid itself, because as I said, sometimes you cannot control the quality of the meshing, and this is mostly the case if you are using any freely available tool. If you are using proprietary software or software that are bought from companies, there you can have more refinement possibilities where you can get better accuracy, and the better refinement is a feature that they sell for certain fee. But what we are using for most of this course is a freely available tool or inbuilt tools. So in this case what we are using is a PDE Toolbox, which is an inbuilt feature of the MATLAB, and we don't have much control on the way to make the grid. We cannot force the grid to be formed in certain way. So in that case we should have a feature of programming it and able to read any data. So let us look at this problem. So what we have as a problem is represented here by this grid. So what I have done here is I have used the PDE Toolbox. I can explain you how the PDE Toolbox works. So this is the geometry of the capacitor. We have used the inbuilt feature of the PDE Toolbox. What it does is it creates a model, and it assigns certain model and it exports the model the way we want. So let's run this one. Let's say we want to see the result for a very basic coarse discretization, and we are going to export this mesh. So you go into mesh, export mesh, you get the variable names as PET. These are the points, edges and triangles. We are exporting it, and once we have exported it, we can go into the save changes. No, we can go into the workspace. So we can save the workspace, we can give it the name, and now let's go into the MATLAB code itself. So the MATLAB code we have used is a FEM code which is able to solve the problem, the Laplace problem, using unstructured mesh. And what it does is it basically reads the data from the PDE toolbox and it sets certain parameters, for example number of nodes, number of elements, number of edges, and these are the values that it reads from the output of the PDE toolbox. The first matrix what it creates is the P matrix, the E matrix is the second one, and the T matrix is the third one. So as I said, the P matrix correspond to the point matrix, the various points in the mesh, E matrix are the edges matrix, and the T matrix correspond to the different triangles. And what is important to know is there are 4 rows and n elements. So the first 3 rows of each column is corresponding to the nodes of the different triangles. For example, each triangle is represented as I, and the first 3 columns are the 3 columns taken in the anti-clockwise. The 4th row contains subdomain information, if the domain is a main domain or part of the other domain. In this case we don't have any subdomain, so we don't need to worry about this. And what it also does is it creates the C matrix, which is the global coefficient matrix that we will be using. And initially what it does is it loads the mesh data. So it prints loading mesh data and it loads the mesh data what we have stored, and it goes and assigns those T, E and P matrix to various parameters. So A3 n elements are the number of elements, basically these are the triangles, and the size of E will be the number of edges, number of nodes will be the size of P, and it displays those values. And what it does is it creates a matrix and defines that matrix as a sparse matrix. The reason for doing that is to make the computation fast, and it creates the source matrix or the source vector to be precise. So it creates the source vector Bj and initializes it, and it displays the computing element coefficient matrix. So it goes into each of the elements, and from each of the elements it computes the value of the elements delta. Delta is the area here, area of each of the elements, and it uses that value into the local matrix, and once the local matrix C is created, it concatenates the local matrix to form the global coefficient matrix, and that is what you see. You see the capital C is the global coefficient matrix and the small c is the local matrix, and once it does that, it applies the boundary condition. As I said, the boundary condition what we are looking into is, as it is said in the initial sheet, we have phi is equal to 1 on the top plate and phi equal to 0 on the bottom plate, and that is what you will see here. We are going to apply the boundary condition as V1 on the nodes of the top plate. So these are all the nodes on the top plate, and we are going to set V2 for the bottom plate, and the value of the V1 and V2 is given on the top. V1 is the upper plate voltage, So we can write them as the potential and the lower plate potential. So these are all in volts, and this is applied in the boundary condition, and we are going to solve the simultaneous equation given by this expression. We are going to compute the various potential V, and we are going to invert the matrix C in order to get the result, and Bj is the source matrix, and the plotted and the computed value of the electric potential are plotted in the figure 1. So let us run this code and see what is happening. We see that the potential is on the top plate going to be 1, and on the bottom plate it is going to be 0, as we can see, and there is a natural degradation. There is a linear degradation from the top plate to bottom plate. Here there is an assumption on the left hand side and the right hand side. The assumption is the fields are going to be following certain physical pattern, as if the plate is infinitely long in this direction and this direction. So it is going to have, assuming that the top direction is y, the horizontal direction is going to be x, it assumes that the plates are infinitely long in the x direction. So the fields values here, the normal component of the fields here are going to be seen continuous, so you do not see any kind of deviation, they are all looking as if the plate is infinitely long. What is also important to know is, once we refine the grid to the level what we want, we can get the accuracy what we want, the way we want. We can go and refine the grid even further. For example, we can go and run this geo capacitor PDE toolbox one more time, and we can refine the grid even further. For example, if you see here, I have refined it even further. This is the maximum refinement possible, but once you refine it so much, what is going to happen is the time it takes for you to run the code is going to take longer. So this is the basic discretization which we ran, and we can go and refine the grid even further. So for example, in this case we can also do the same thing what we did before, export the mesh, we can say OK, and we can exit, and what we can see is, in the previous case when we did the computation, we had 177 nodes, 312 elements and 40 edges, but now we have refined it so much, we expect that the number of nodes, number of edges are going to be dramatically higher. So let us go and save this particular matrix data. So we are going to save it once again, the same name. So mesh data capacitor, replace, and now we are going to go and run the program one more time. So let us go and run the program FEM unstructured grid one more time, and it is going to take a long time because there are going to be so many elements. So let us run it, and as you can see, the solution is going to take a long time. So it is very busy now, it is computing the element coefficient matrix, and as you can see, compared to the last time, it is going to have 640. Earlier we had only 40 edges, now we have 640 edges. This is a much finer discretization, so it is going to take a very long time for us to get the result. What I wanted to show is, in certain problems it does not really matter how much cells you are going to have, because the solution itself will be symmetric, and you can use the symmetry of the solution to get a better result in a quicker way or in a very easy way. In this case, I have done the problem so as to show you how one can use PDE toolbox and combine it with finite element method and as I said, this grid is going to take such a long time. It's still computing the coefficient matrix, forming the global coefficient matrix, and once it is done, it is going to show the result. And let's see what is going to be the difference between a coarse grid what we had and very fine grid, and does it make sense. And as I told you, one of the things that one has to learn during the process of this lecture is how can we make an informed choice of the discretization, the method that we are going to use, and the kind of resolution that we want. For example, if you see this solution what we have got, we didn't gain anything that much. If you see the result what we have got here looks very similar to what we have got even before. Because the problem itself is very symmetric and it's a straightforward problem, there is not much material discontinuity or material changes, permittivity and permeability changes, or domain itself is not that complicated, so we are not gaining that much. So we will do yet another problem using the same finite element method, and we will see how the discretization going to improve our accuracy in that case. So with that being said, we will stop here. What we have seen is a very simple Laplace problem. We have used an inbuilt mesh generator called as the PDE toolbox, and we have used nodal based FEM method using unstructured grid to solve a very simple Laplace problem, and we have seen how the accuracy is going to change, whether it makes sense to go for a finer grid or coarser grid, so on and so forth. And as I told you, in the next module, in the next exercises, what we will see is a very different type of capacitor problem where refinement helps us in gaining something. So that's the focus of the next module. See you in the next module. Thank you.